Hello, brave calculus students, and welcome to AP Calculus BC Unit 10, Sequences and Series. This is generally what people think is the hardest part of the BC course, and totally the only reason why it's its own class. But I'm here to tell you that it makes way more sense than any of the other stuff. This involves a big mindset shift. You have to stop thinking about integrals and derivatives and doing all of these little rules to find the slope of lines. This is an entirely different thing with a lot less visual elements, and it involves a very different way of thinking about infinity. But it is very much still calculus, and you can think about it, and it does make sense. So let's start off with the basics. What is a sequence? In the AP Calculus videos, they call them, I think, a sequence is an ordered list which you can index into, but that's a little bit specific. A sequence is a list of numbers that is in sequence. It just means like a list. That's not that bad. Any list of numbers that is in order is a sequence. It doesn't even matter what I wrote. I think I wrote things that go up by 2. You can represent a sequence by this list of numbers that goes on forever, or like a function, you can represent it by like a general term. Where a function, you'd write f of x equals something. For a sequence, you would write that a sub n, some general number, is, I believe this is 1 plus 2 times n. And what this means is n is the place you are on the list. So this is the 0th place. That's a little confusing. This is the 1th place, the 2th place, etc. So you'd start at the 0th place. You'd say, OK, n is 0. That's our place in the list. So the first thing, the 0th place, is 0 plus 1 is 1. When n is 1, it's 3. When it's 2, it's 5, etc., etc. So it's just like a function. And if we graph it visually, you can see again that it's just like a function. If we were to graph the corresponding function, f of x equals 1 plus 2x, that'd look kind of like this. And if we were going to graph this sequence, it would look like this. It's just like the function, but it's only at the whole numbered increments. And that makes sense because there isn't a 1.5 entry in the list. There's the first entry, second entry, etc. And so you can think of these either as a list of numbers or as like a function with all the icky fractions taken out. So it's actually simpler than most of what we've been working with. A series is just the next step. You look at a list of numbers and you go, oh boy, that sure is a list of numbers. What can we do with them? Not much. A series is just adding them up. Like, if you want to take the sum, which you represent with this big S, of all the terms of a sub n, which is what you'd call this little subscript, you'd pronounce this as a sub n. If I want to add up all the terms up to where n equals 2, I'd say the sum up to n equals 2 equals 1 plus 3 plus 5. Or, more generally, a sub 0 plus a sub 1 plus a sub 2. And so you can say this is a sum. They call it a partial sum because it's just not the sum of the whole series. It's the sum of this part of the sequence. The partial sum of a sub n up to n equals 2 is 1 plus 3 plus 5 equals 9. And then you can do this for maybe a partial sum up to n equals 3, or n equals 4, or n equals 5. And all of these are just numbers. It's just adding up a different number of terms in the list. But this is calculus. We hate real numbers. And so we're going to go up to infinity. We're going to say, what if, so we can add up the first 5 terms. We can use this summation notation to say from n equals 0 to n equals like 5, add up a sub n, which is the same as saying s sub 5. You've seen the summation notation before. This just means you count up through this list, adding up each one. You've seen it in Riemann sums, which will become important later and is part of why we do this in calculus. You can calculate s sub 5 like this. You can calculate s sub 6 like this. But what if we want to go to infinity? Well, now this is a little silly. Why would you write s sub infinity? Because what you mean when you're writing s sub infinity is what is the sum of the entire sequence, the whole thing. If you keep going forever until you've run out of sequence, what is the whole sum? And so generally, they just represent this as s, like the whole sum, not any partial sum, just the sum of the series. And you'd write it like this. But we still don't really know how to deal with infinities. A lot of calculus, you're given infinities, but they don't really want you to like actually plug them in or touch them too much because they're not real numbers. And so this can also be represented as the limit of a partial sum with n terms as n goes to infinity. Because this is what calculus is all about. You're given a really big number and some really big scope. Like, if we want to slice up an integral into a bunch of different parts, like a Riemann sum, but we want infinite different parts, you can't just plug in infinity because infinity is too big to just plug in. So we're approaching it. We're approaching it with a limit. This is the whole idea of calculus. This is what actually relates, like, derivatives, which is looking at an infinitely small change in slope. Integrals is looking at infinitely many slices of a function. And this is even simpler than that. Like, those all involve like some levels of like abstraction mentally, but the only thing that you're adding up here isn't like infinitely many function slices. You're just adding up a really, really long list. So this isn't really that different from what you're doing in calculus. You're just doing it in kind of like a different format, and some might say a less complex format. So this limit, as n approaches infinity, of s sub n, the partial sum with up to infinity terms in the sequence, can then be written like this, which also is just what we call the sum. And you might be thinking, well, that's kind of pointless. Our series is like 1, 3, 5, 7, 9. If we keep adding up 1 plus 3 plus 5 plus 7 plus 9 plus 11 all the way up until we're adding infinity, that doesn't tell us anything. That's just infinity. That's just really big. But sometimes, counterintuitively, adding up an infinite number of things does actually make a finite number. And while in concept that doesn't really make sense, like those words don't like to fit in our head very much, you know about this, and we observe it fairly regularly. It's the most like common visual math paradox you can find. This is kind of, this black marker is a little bit tough. Okay, let's think about a series, the same kind that we just looked at, where we're saying the general term, the way you represent this series, is a sub n, so any term n of this series can be represented as 1/2 to the nth power. And this is a sequence that you've probably seen before. It looks like this. If you've ever done math team, this is a nice geometric sequence. And we'll talk about geometric sequence more, I think, in the next video. So A is this sequence. It looks like, well, it actually looks like 1. But I'm going to ignore the 0th term. We're going to start this at 1 because it looks a little prettier when in the demonstration. 1/2. 1/4, 1/8, 1/16 dot, 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 dot. So this is a similar type of series as we looked at before. It follows this rule, where all of these terms follow a rule, and you just keep listing them onto infinity. And if we want to take the sum of this series, like the sum of the first, what is this? 1, 2, 3. S sub 3 would be 1/2 plus 1/4 plus 1/8, which is, see, this is 2/8, this is 4/8, this is 6/8. That's not right. 7/8. And so that can be represented as the sum from n equals 1, because I'm starting with 1 here, to infinity. Nope. To 3 of a sub n. And you can see how this kind of this doesn't get super big. This isn't really that much bigger than 1/2, but it still kind of looks like it'll build up forever. But if we look at this visually, we can make this into a nice little number line. Let me now present a scenario. You have a distance, and you don't really want to get there very fast. You're kind of dilly-dallying, like maybe you have to get to class. And so you're like, okay, well, I'll just go halfway. Oh, but now you're so close, and you don't really want to go all the way still. You're like kind of ditching out. And so you just go halfway again. And then again, and again, and again, and again, because you're getting ever closer, and you don't want it to come. And so you then go 1/8, and then 1/16, and then 1/32, and then 1/64, and then you realize that you never actually get there. If you go half the distance, and then half of that distance, and then half of that distance, there's always another half to go. Like, you're never actually going to get all of the way. And so what this is saying is no matter how many powers of 1/2 you're adding up, as you approach the infinitieth step of your little journey, you're still not quite at 1. And so in math talk, we're saying if you approach but never quite reach something, that the limit as n approaches infinity of s sub n, the little sums of a sub n, is 1. And so what we can say, counterintuitively, is that A, this infinite list of numbers, when you add them all up, the sum actually equals, because in calculus, the limit does mean it equals. The sum of all these numbers is finite, and it equals 1. So you can say S equals 1. And that is what all of sequences and series is about. It is about this phenomenon where an infinite number of stuff equals 1 stuff, or a finite number of stuff. This is called convergence, because if you add up like that list of 1, 3, 5, 7, 9, they're going to grow and grow and grow all the way up to infinity. And so you can say that the sum is diverging. This sum, even though you're adding infinitely many stuff, it's getting closer and closer and converging on this value. It's converging on 1. So for the rest of this course, we are going to talk about how to figure out if an infinite list of numbers converges to a finite sum. And there are a lot of these funky little tests that you'll learn about hopefully in your real class that probably don't make any sense, and they probably don't explain them very well. And so I'm going to try to make them make sense in a real-world context. Thank you. Have a nice day.